Hello, can you?
Yes, we can see your slides. I don't think you can hear me.
See your slides, right? Based on...
Can you text them and say yes?
You can see my slides now. Okay. Great. All right. I apologize for the delay. I'll try to be a bit quicker. So thank you so much for accommodating a remote presentation. I'm Fedchin. I'm a PhD student at Tufts University, and I'm going to talk about test generation Dafny'. And in particular, I'm going to talk about scaling up existing test generation functionality to system-level tests. And this is a joint work with my advisor at Tufts, Professor Jeff Foster, and with my mentors at Amazon, Zvonimir, Rakamaric, and Aleksandr. So I'll begin by motivating the need for runtime tests in Dafny' in general. And then I'll move on and introduce DTest, the Dafny' testing toolkit, which allows Dafny' users to automatically produce tests from implementation written in Dafny'. And then I'll move on and talk about scaling this functionality up and the challenges that we face when trying to produce system-level tests. So the main question, sort of the first question that everybody asks when talking about runtime tests in Dafny' is why cannot you prove everything that you want to hold true about the behavior of your program at runtime? Why cannot you prove it before compile time? Right? This is what verification is about. So why do you ever need runtime tests in a verification of these things? And so there are sort of three answers. First, you might want tests before you have completed verifying your program. In particular, imagine a situation where you have written an implementation and you have written a high-level specification that tells you what this implementation is supposed to do. But you haven't written any intermediate pre- and post-condition, any loop invariance. The verifier cannot yet give you that proof, and you have to do a lot of work before that happens. And in this situation, the worst that can happen is that you go in, spend hours and hours and hours writing your proof, and then figure out that your implementation actually has a bug, meaning you have to write everything, and the time you spent working on your proof is wasted. And so in this case, what you could imagine doing first at hand is to generate runtime tests from the implementation, and then at runtime check that at least for some comprehensive set of inputs, your implementation abides by the specification. And then once you know that, you can go on and actually write proof and then get the verification guarantees. Now, the second reason to use runtime testing is that no true end-to-end verified infrastructure exists, meaning that even though Dafny' code is verified, when you compile your Dafny' code, you might be actually connecting to some standard libraries in the language you're compiling to, or you might be using projects written in the language you're compiling to that have not been verified, and so it is possible bugs exist in both, to exist in those projects, and so you might want to generate random tests that would sort of give you additional assurance that the whole pipeline is correct. And finally, Dafny' is often used for model-based testing. So this is a situation where you already have an existing implementation written in another language, and then you write the Dafny' model, and then you might be absolutely certain that your Dafny' model is correct, but you still might want to generate tests from the model to run on that implementation that's written in another language that you don't actually have guarantees about, and this way you can perform model-based testing. Okay, so these are the reasons why you might want random testing in Dafny'. So now I'm going to introduce DTest, or Dafny' testing toolkit, that allows you to generate random tests. And this has been presented last year at NFM originally. So in a nutshell, what DTest does, it takes a Dafny' program and it produces unit tests. And it does this by inserting failing assertions, or assert false, at some location in the program, and then asking Dafny' to verify the correctness of the program. Now, of course, if that assertion is at all reachable, Dafny' is going to complain that assertion might be violated, and it will give a counterexample. And then from that counterexample, you can extract inputs for a test method, and then repeat that process for a different location in the program, and thereby create tests. So to give a concrete example, you can see here on the left side of your slide, there is a function that computes a maximum of 2 numbers, and it has 2 branches corresponding to which of the 2 arguments is greater. And so if you run DTest on this program, you will get 2 tests that you see on the right hand of your slide. So as you can see in the first one, the first argument is greater, and then on the second one, the 2 arguments are equal. Now, DTest can handle much more complicated constraints. So now on your slide, you see a snippet from a program I have written that defines a subset of chess rules in Dafny'. And so these definition of these rules allow me to check if a king is under check for a particular configuration of pieces on the board. And so this is what the code on the left-hand side does. It takes as input a configuration of pieces on the board, and then it tells you whether or not the king is under check. So there are still 2 branches, just like in the example that I showed earlier, but in this case, the conditions that guard the conditional are much more complicated, and they involve recursive and functions and nested predicates, and then the input is also more complicated, right? So it's a nested data type. But DTest can still handle it, and you can read more about it on the Dafny' blog. I have a link on the slide. I'll have a QR code. The point is that the DTest will be able to produce configuration of pieces on the chessboard as hypothetical inputs, and you can see some of them on the slide. So now let me move on to system-level tests and scalability. So to motivate doing system-level tests, imagine this use case that I mentioned before of writing a model in Dafny' to prove some properties about an existing implementation, and then trying to prove the equivalence of the model and the implementation by generating tests from the model. So it is a safe assumption to make that the entry points for the two programs for the model implementation are equivalent in some way. So they take the inputs of the same form. But the details of the implementation, the helper functions and methods might be different. And so what you really want in this case, if you really want to generate tests, you want to generate system-level tests, such that they will use this entry point, which we can assume is equivalent in both cases, and then cover the entire program. And so that's why we want tests that generate inputs for one method, but cover the entire program and all the methods within. And another sort of benefit of system-level testing is that it can help you identify dead code of a particular type. So specifically, I'm talking about dead code that is dead not in the context of a particular function, but in the context of a program. So here you can see the predicate threatens that I've written as part of the example I mentioned before that involves chess. And you can see here the line highlighted in red is dead with respect to the program because it talks about the way a king, the chess piece, can threaten different positions on a chessboard. But the program itself is designed to reason about situations in which a king is under check, and one king can never put another king under check. In chess, that can never happen, and so this predicate is in fact never called with king as a receiver, and so this line is never going to be executed. And DTest can tell you that, and tell you that it's provably so, unlike say a fuzzer that will just not be able to generate tests in this use case. Now, to enable system-level tests, we had to redesign some parts of DTest because by default, Dafny' performs verification on a method-by-method basis, meaning that when it looks at a method and tries to verify properties of that method, it only has access to specifications of other methods, but not their implementation. Whereas we want to generate inputs for one method, but also cover parts of the implementation in a different method. So the way we went about it is we essentially use a form of above-normal checking through inlining. So we can inline bodies of methods into other methods. And because in general inlining is costly, we also allow the user to guide this process to specify which methods should be inlined. You can, and I'll not go into details right now, but this involves some engineering challenges, and particularly removing short circuiting from Dafny to make this work. But let me sort of jump into motivating why we need user-guided inlining. You can see here on the slide an example of a call graph for this example that I keep mentioning. It involves chess. In particular, on the left top corner, you can see the describe method that I previously showed you. And then on the bottom right corner, you see this map absolute value function. And my point here is that for 120 paths to this function for this fairly simple program, and it does not account for branches within the methods themselves, so the number of paths we could control for would be much higher, for example. And so the idea is that if you try to inline the absolute value function, the test generation will take much longer, but the user can explore this trade-off between coverage and speed by specifying that they do not want, for example, to cover all the different paths to this absolute value function. All right, I know I'm running a long time, so I'll say that you can read more about this particular example and how to solve chess puzzles with Dafny on the blog post, and very quickly about some open source results. So we did use the test to generate runtime tests for existing Dafny projects, in particular the Dafny toolkit library, which is currently being transformed to the Dafny standard library, and also on the AWS Encryption SDK. So we generate hundreds of tests, and we achieve coverage, fairly high coverage, both statement and branch coverage, and you cannot achieve 100% in these use cases. So the numbers are somewhat higher if you account for that. And yeah, I want to thank everybody who has been involved in test generation for the past several years, and this is it. And I'm happy to take any questions. I cannot hear anything though, so let me know if you can. Let me try and join the
Okay, well maybe people can send messages on Discord to Sasha or email Sasha.
Just talk into the mic.
Well, we tried earlier and he wasn't able to hear us when we were talking to him before, so.
Through the mic?
Yes. Maybe we could try again though.
Sorry.
Hello?
Can you hear us?
Hello? Can you hear me?
Can you hear us? Apparently not. I'm sorry. Yeah.
It's not clear it's on your end or on his end.
Hello? I can hear you now I can hear you now through the YouTube stream. Hello?
Oh, it's through
I
the
can
YouTube?
hear you through the YouTube stream.
Okay, that's...
I can hear you.
Okay.
So do we have any questions? Yes, please go on.
Hi, thanks for the talk. I was curious a little bit about the, I guess, one step in your process where you go from a counterexample to a test, or like getting the inputs that cause this particular counterexample to trigger, and maybe just what that process kind of looks like, because I know Dafny counterexamples can be a little hard to parse back for more complicated examples.
Communicate with outer space.
Alright, maybe,
Okay.
Right, thank you. I assume there will be a bit of a lag, so I'll answer this question and probably then it'll be last one. But yeah, so this is the main part of test generation, and essentially what we have is a model that Z3 gives us, and then we have to convert it right to Dafny syntax. It is essentially. Oh, sorry. Sorry, there was some very sharp echo. Anyway, I'll wrap up by saying that this is a problem that I'm still working on in making the functionality better, and that a major challenge is preventing incompleteness, right? So sometimes the counter example can be incomplete, so that's sort of the main challenge, but it mostly has to do with how we write Dafny code rather than with content example extraction itself. Thank you.
Okay, Okay, our next talk is also about testing, although of the Dafny compiler as opposed to testing particular Dafny programs. This is going to be a jointly delivered talk by Alex and Dylan. Thank you. Yeah.